We'll try that. Very good. So as I was saying, so I'm from Echelon originally, now part of Adesto, but we're still doing very much the same thing. We're still very committed to the embedded controls industry, the HVAC industry. So the things that we've been doing from the beginning in terms of creating a very intelligent networked controls, we're still very much in that business, and we're focused on that. But what I want to talk about today is something a bit broader than that. Talk a bit about control networking and automation in the IoT age. Right. So we're going into the age of IoT. Things are very, very much changing in our industry, and I want to talk about how they're changing and how we can change them further for the better. So IoT has a promise of delivering great value to your customers, to your systems. Some of the value that IoT promises are doing services like energy optimization, where you can make a building more efficient and use less energy over time and save the owners money in terms of how much they spend for energy. Another one's predictive maintenance, that IoT promises to be able to monitor machines. And by monitoring machines and knowing how they're changing and how they're operating, you can predict when they're before they fail and send out service technicians to repair them before a failure occurs, making systems more reliable. Another promise of IoT is more efficient space utilization, right? Because IoT systems can monitor how space is being used within a building, and depending on how it's used, more effectively assign rooms, for example, for meetings, or help with planning for where people are going to sit, and more effectively use the overall space. And finally, personalization and productivity. Because IoT is cloud connected, there's a promise that you can have all the users, all the occupants in the building cloud connected, and they can have control over their space. They can have control over the rooms that they use, and how they schedule their meetings and other group activities. So that's the promise of IoT, that sort of thing. And more in the future, more taking advantage of artificial intelligence and data analytics to more efficiently use a building. And building owners are starting to ask for these things. Integrators tell us all the time that the building owners really want these capabilities because they hear about them. They hear about the IoT, they hear how they can have all these great services, and they want to know, how do we get them? But the challenge is, you look on the left, it's sort of a typical building, right? And if you look in that typical building, there's often a large mixture of different kinds of protocols that are in use to interconnect the devices within the building. So you have protocols like LAN, we're part of LAN-MARC, protocols like BACnet, but there's also newer protocols too, some of the IoT protocols like Zigbee, like 5G, like Bluetooth. All those protocols are coming in, and we're starting to see buildings where all these things are mixed together. They're often in different subsystems. So fleet management might be one protocol, fire and safety is another, security is another, HVAC is another. So they tend to have one or two protocols per subsystem. But then you bring all these subsystems together, and you have this real mix of systems. And the problem is, that no one's going to go in and rip out all those systems and put in one protocol to interconnect everything in the building. You're going to continue to have multiple protocols implementing multiple subsystems. So backward compatibility is absolutely required. We can't say you don't get these great new services like energy optimization until you rip everything out and put a new system in. We have to deliver a solution that delivers this value on top of those existing systems. And we know these systems have very long product cycles. If you look at the major players in our industry, the companies like Honeywell and Johnson Controls, Siemens, have very, very long product cycles. So to say, oh yeah, you guys just need to switch to a common protocol, that's just not going to happen in any sort of reasonable time frame. And failure of these systems can be very costly, especially systems like fire and safety and security. If that system fails, even HVAC, if the HVAC system goes down and the building can't be occupied, It's very, very costly for the owner. So we need those systems. We need those systems to stay in the protocols that they are. And yet we need to somehow figure out how do we deliver all this value. So the way that that value gets delivered today is by adding a lot of cost. Sort of the first step is you go through network integration, right? So now we have all these networks, all these different protocols. Well, we can put gateways between them and try to interconnect everything. That's a very, very costly proposition. It's very time intensive, takes a lot of work from the integrator. And the integrators have to understand the multiple protocols, right? Because if you're trying to get a Bluetooth device to talk to a BACnet device, you kind of have to understand both ends, or someone has to develop a gateway that understands both ends. Second, there's data integration. You know, each of these systems has a very different way of representing their data. You know, LAN has a very rich data model that characterizes all the data in the system and makes it easy to interconnect all the devices to the services that they need. BACnet has another data model that does some similar things. You know, Bluetooth doesn't have much of a data model. Modbus, not much of a data model. So the data models are either there or they're incomplete, but getting all that data integrated into common services like energy optimization is a challenge. Again, it's like the network integration challenge. You have to do all the translations from the data model of the underlying protocol to the data model of the service. And finally, what's often required to solve those two problems, to solve either the network integration problem or the data integration problem, what's often required is custom applications. Someone has to sit down, write some custom code to ingest the data, to ingest the network information, translate it, transform it, send it off to another service. Well, that's costly as well. And that really eats into your margins as integrators trying to install a building. If you're spending all your time doing application development, that's less profit for you. So here's the promise we're trying to get to. And yeah, with a lot of investment, a lot of cost, you can get there, but it's difficult. But the problem actually gets worse than that with IoT. And how's it get worse? It's what I call IoT cloud silos, and I say those silos are really bringing on the tiers of the IoT. Because IoT is this promise, right, of something, these great services running in the cloud, these great services talking to all the devices in a system, such as a building automation and control system. But what really happens today is each one of those subsystems has their own cloud application. So the fleet management application, yeah, there's a nice cloud application to manage the fleet, but it doesn't talk to anything else in the building. The HVAC application, you can get IoT-based HVAC applications, but they only know about the HVAC system in the building. They don't know about the rest of the building. Security is the same way. We can have cloud-based security. The security system, yeah, knows all about the occupants of the building and who's going in and out, but it doesn't talk to the other systems. So you have all these clouds out there, so it's not just one IoT cloud. And actually can get worse for some of the richer protocols like LAN or BACnet. You can have multiple subsystems within a LAN network or multiple subsystems within a BACnet network. And each of those subsystems may have their own cloud applications. But again, those don't interconnect with each other. So now you have a tremendous problem, right? That all these clouds are out there and they're not communicating, just as all these subsystems are in the building and they're not communicating. Now you could imagine that every cloud is connected to every subsystem, but you don't really want to do that. I mean, that's just lots and lots of X's on this chart, right? The chart becomes much too complicated. It's not practical to interconnect every IoT application with every device in the building. So how do we solve that problem? We want to deliver solutions, not worry about just the problems, right? So the solution to the problem is to create what we call a data and services fabric. So think of a fabric as having lots of threads that go all over the fabric, right? And so a fabric is like this great interconnect between all the things around the fabric. And we can do the same thing within a control system. We can create a fabric that interconnects all the data within the control system and all the services within the control system. And by doing that, then, we can make all these things interconnect with each other. We can have all the devices within the building communicate with each other, and communicate with the services that they need, and send the data that they need to the cloud, and yet do that universally so that every device is connected to every other device, every device is connected to every service. So that kind of gives us three key things. The first is connectivity, interoperability. We want to bridge all these physical media. Our example building, we had Bluetooth, we had LAN, we had BACnet, we had 5G. Those are all, often different media, and we can bridge between them so that the LAN device can talk to the BACnet device, can talk to the Modbus device, can talk to the Bluetooth device. And it can cross between the more traditional protocols like LAN and BACnet, the newer protocols like Zigbee and Bluetooth and 5G. We can connect them all. It doesn't matter which protocol it is. But just making things talk to each other isn't enough. They have to understand each other. Just like two people talking to each other, it doesn't do very much good unless they speak the same language or there's some translation between them. And so that's data interoperability, right? We need a way that when, say, a Modbus occupancy sensor sends information, the BACnet or LAN controller understands that information, understands it means occupancy. So we need data to move smoothly through the system and to be understood wherever it goes and wherever it comes from. And that has to be completely independent of the protocols because we know there's many protocols in there. So data interoperability is a key part of the fabric. The fabric just won't work. The line between those two devices won't do any good unless the two devices understand each other's data. And so that's a key part of the fabric. And then finally, this interoperability of the services themselves. So services that you're used to putting into building, things like scheduling, logging, and alarming. When you're creating a schedule for the building, you want that schedule to work with all the devices in the building. So if I have that mixed-use building, that's LAN, BACnet, Modbus, Bluetooth, 5G, I want the schedule to be able to schedule anything there. Same thing with data logging. I want to collect log data because ultimately that's what I'm going to be sending to analytics services and AI services. I want to collect that data from all the devices in the building. Again, independent of where those devices are, what protocol they're using, how they encode their data. And same thing with alarming, right? I want to monitor all these devices. If anything fails anywhere, I want to know. If anything is generating data that's above a limit, I want to know. And again, that needs to be independent of the protocol. And so that's the purpose of the fabric. So the fabric kind of interconnects things at two levels. At the bottom, you see all the different protocols that may be in use within a building, the ones we've talked about, like the wireless protocols, the 5G protocol, might be a private net mesh, there might be a low power WAN in the building, there might be a wired FT network for LAN, there might be an Ethernet network for BACnet, excuse me. So that's all the devices in the building at the bottom, all implementing different protocols, all intercommunicating. They go into the fabric, they connect to each other, so I can connect those devices together, and they also connect upwards to the services. So the services at the top are things like data services, collecting that data, logging the data so that we can look at it later. It might be services like artificial intelligence services that are sort of monitoring. That's where the predictive maintenance comes from, and by looking at that data, we can predict when failures are going to occur, or we can monitor energy usage to try to optimize energy usage. There's network services. The network services are how you're going to interconnect these things together. And actually, even before that, it's how you could put them into a network, how you could set up the communication between devices, and then allow the devices to communicate with each other and also with these other services. And automation and control services, right? We want to create the sequences of operations for the building, and those sequences, though, need to be able to apply to the different subsystems. So I can include an occupancy sensor both in a lighting system as well as the HVAC system, because both need to know about occupancies, so I can provide that through automation and control services. And finally, I can take those services up into building management systems, the single pane of glass that sees the entire building, that sees all these subsystems, and provides the user with control over the subsystems and allows them to create a single interface for the building operator. And most importantly, those services may be anywhere. If you look on the right, there's services within the building, right? So I want a building management system in the building for the building operator that is working within the building. But on the left, I want similar services, maybe the same services in the cloud, so I can access those services from anywhere. And some of the newer IoT services, such as services available from IBM Watson, those are always located in the cloud. Right? So I want to take this data from all these networks, from all these protocols, and either push them out to the cloud or push them locally within the building, and have services that potentially are the same thing or potentially different between the local network and the cloud network. So that's what the fabric can do for us. The fabric can provide that connectivity between devices and between services. So then you might ask, well, so what about other web services that are out there? There's many solutions today for the IoT for different kinds of web services. And I just noticed this chart is actually labeled backwards, but I'll explain it. And if you look at how different protocols compare to each other, there's kind of two dimensions to it. One dimension is field protocol flexibility, right? Because there are services today that are built on top of individual protocols. There's services built on top of LAN, there's services built on top of BACnet, but those services tend to be tied to the protocols they're built on top of. So they might provide cloud access either to a LAN device or to a BACnet device, but they don't provide easy access to devices using other protocols like we described. You can provide that by adding gateways, right? So if I'm using a BACnet cloud service, I can create gateways that go to all these other protocols, but now I'm constantly developing new gateways for all these new protocols. So the field protocol specific services are good for their protocol, not so good for other protocols. But the other dimension is sort of data and services integration and completeness. The problem I was talking about earlier, that if a different protocol has a different way of representing a data point, for example, a room temperature data point versus an outdoor air temperature data point versus a supply air temperature data point. If they all have different ways of representing that data, when you bring it all together, how do you understand it, right? So a really good web services model is going to provide a way to keep the richness of the data so that a supply air temperature data point is a supply air temperature data point. It's not something else. So that's the key thing. We got to keep the understanding of what the data is, what the semantics of that data is, how the data is used, where it's used, what's it applied to, where is it applied to in the building. And so that's the completeness of the data model. And so if you look at general purpose IoT web services, things like you would see in AWS Greengrass, right? That's an IoT protocol, good for moving data to the cloud, but very little understanding of what that data is. It's up to the integrator to figure out, well, how do I translate my supplier temperature data point into something that Greengrass understands, and into something that the services that are using Greengrass understand. So IoT protocols tend to be good at moving data to the cloud, not so good at understanding the data. And field protocol specific services are good for moving data to the cloud, but not so good at understanding more than one protocol. So what we're proposing for Lawnmark is something we call IAP, for the IoT Access Protocol. And the idea of the IoT Access Protocol is, first of all, to provide that data fabric and services fabric I described earlier, which connects everything to everything. But second, to solve both of these problems. So first, make it field protocol independent. So it's not based on LAN, not based on BACnet, not based on Modbus, not based on Bluetooth. It's a web services protocol that's absolutely protocol agnostic. So that's the first key thing. So protocol independent, but protocol independent while retaining the richness of the data models and services models of the underlying protocols. You know, BACNet's got a great services model, great scheduling, great trending, great alarming. We want to preserve all that. So you need a web services protocol that understands all that, understands priority. Right? Lawn has this great data model, this great functional profiles, great standard types. We need to preserve all that. So that's the objective of IAP, right? Of the Landmark Web Services Standard, is to solve both of those problems. So you get two parts to it. First is the data model. So what's the data model? So first is data types. So if you're familiar with LAN, you know LAN has a very rich data type model, the standard network variable types, standard configuration property types, standard enumerations, standard formats. That's the data model. And we can take that sort of data model and apply it to all protocols. So you look at a protocol that's sort of the opposite direction, a protocol like Modbus. You know, Modbus doesn't standardize anything, right? It just standardizes how do you represent an address for a data point in a device, how many bytes that data point is, and that's it. I mean, that's what Modbus defines. But you can take a data model like the LAN data model and apply it to a Modbus device. So if I have a temperature value represented in the device, I can specify what that data type is for that data point. And now as the data flows through the system, I know it's a temperature, I know how it's encoded. So that's the data types. Data semantics, you know, what's the meaning of a data point? So, you know, knowing something's temperature isn't enough. We need to know, for example, if it's a room temperature or an outdoor air temperature, or a supply air temperature. So that's the semantics. What's it mean? How's it used? And we need to preserve that. And so protocols like Landmark are great at representing data semantics, and we need to carry that semantics with the data. Finding data priorities. You know, priority management is something that BACnet does very well. It's got a priority array where you can specify the priority of an update so that a life safety update coming in from the life safety system overrides the setting of something that was specified by the control system. That's something we need to preserve and support across multiple protocols. So make it so it's not just a BACnet thing anymore. It's actually a common web services standard for priority management. Next is device interface definition. You know, to make semantics possible, you need to understand what the devices are. You need to understand what sort of device a device within the system is, and have a standard way of representing that information, providing that information to the web services interfaces, all the way through that fabric. And that's something that BACNet's always been very good at. BACNet's good at discovering device types, good at getting device information from the devices over the network. We need that capability for all device types. Then there's configuration data definition. Same problem as operational data, but configuration data are things like set points. You know, sometimes we want to set a set point for, say, a temperature for a VAV controller. We need a standard way of representing those data types as well. So there's operational data like temperatures, but configuration data like set points, and that needs to be part of the data model. And then finally, data flow definition. We want the data to flow through the system. I want data, say, to flow from an occupancy sensor, both to my temperature controller, as well as my security system. And we want to define those data flows. And those data flows may be going between different protocols. And that's okay. That's part of the data model. Then there's the services model. And services is a very key part of the overall Landmark Web Services. It's not enough to just move data. In traditional IoT systems, that's what they focus on. They focus on moving data to the cloud and figure everything's going to happen in the cloud. So just get the data there and you're done. But that's not enough. We need some standard services too. The first one being device discovery. How do we find the devices in the system independent of what protocols are running? And then once we find the devices, how do we provision them? So it's device provisioning. We want to be able to find the device, provision it, tell the system the device is there, tell the system what its interface is based on that device interface definition. Then we need connection management to provision the device, to tell the device where do you send your data, where do you get your data. Then we need the three big services that are very common within building control systems, the scheduling, the logging, and the alarming. So that's the standard services that need to be standardized at the web services layer so that you can have web services applications that are doing things like scheduling the system, logging the data from the system, generating alarms as alarms occur. So let's take a little deeper dive then and look at that data and services model, because we want to make sure that this model is going to apply to the full life cycle of the building. If we look at the life cycle of the building, often IoT applications focus on one part, which is kind of down here, the system integration piece, right? They focus on getting the data, moving to the cloud, doing things like analytics and AI. And so that's sort of the operational part of the life cycle. And of course, it's a critical, important part, and it's where we want to get to. But it's not the whole life cycle. And so if a web services standard doesn't address the whole life cycle, it's not going to succeed. And if we look at that, we can back up from that first, from the system integration piece and look at what leads up to it. What do you have to do to get ready to integrate your data? And it starts with the planning phase. There's a planning phase early on in the bid process where you're defining, what are the networks going to be within the system? What are the devices going to be within the system? How many devices are there? Where are those devices? How are they located? How are they connected? And so there's a planning phase that's very critical. And that planning phase needs to lead right into, ultimately, the system integration phase, right? Because that's where you're defining the system. You shouldn't have to define the system multiple times. You should be able to define it once. You can refine that definition as you're going through the bid process. But in the end, you're going to have to define the device types. You're going to have to define the design of the system and how they're interconnected, and then take that information forward into installation when you actually create the edge servers within the building and have them intercommunicating, and provisioning when you're discovering devices and configuring those devices. And that's all part of the early phase of the system when you're first building the network up. And finally, when you get through that top row, now you have an operating system. Now the devices are communicating, the services are there. And now you can really do the system integration then. Now you can take the data from those devices, push them to those cloud services, and get the value of IoT that you're looking for. And then finally, you can hand off the system and start maintaining the system. Let's take a little deeper look at the open architecture, because we as Lawmark, that's a critical part of Lawmark, is we're all about openness, we're about open systems. And what's it mean for an open system based on IoT and standard web services? And we need to be open in three different directions, right? So one is openness up to things like cloud IoT platforms, web services, advanced analytics, AI. And so the interface then from the system into those cloud applications and services needs to be fully open. We need to be open to the bottom left, which are the actual interfaces to those field devices, whether those field devices are IoT devices or traditional devices like BACnet or lawn devices, or even industrial equipment that has a smart interface. And finally, openness to the bottom right, which are to the control systems, the building management system, the configuration management system, the supervisory control and data acquisition systems. All those interfaces need to be open and can be provided by the Lawmark Web Services standard. And what's really key about this is, since it is a common standard going all three directions, it means many of these services, many of these capabilities can actually be provided anywhere. And so if we look at services such as analytics and AI, right? That's sort of the traditional IoT applications, IoT services. Well, we can have analytics and AI running right in the edge devices. We can have analytics and AI running in the building management system, and we can have analytics and AI running in the cloud. There may be different scales. An analytics engine running within an edge device might be small, simple, just looking at what that one device is doing. An analytics application running in the cloud is going to have access to a lot of data from a lot of systems, from a lot of devices, and may be able to provide a much more rich interface. But the point is they're all using the same common data fabric, and I can move them anywhere between the various systems. Some applications are better to have local. So such as bottom right, the operational systems management. You may want to have operational systems management local to the building management system or the configuration management system. And automation controls, often you might want automation local, but you could have some supervisory kind of automation running in the cloud. So an open web services standard makes this possible. It makes it possible to interconnect everything, and it makes it possible to host these services anywhere. So where are we? So we're developing within Landmark a web services standard. We have a draft for that standard. Here's the first few pages of it. That a Landmark Web Services task group is working on to define those services, to define that data model, to define the data and services fabric, so that we can bring the promise of IoT to building management systems, to building control systems. And we'd like to ask you if you're interested to participate in that development. So we're in the early draft phase. We've done a lot of work to create the draft, to create the proposal, to create the standard services, to create the standard data model, to define how this can actually work. How can we really create a data fabric that can flow from edge devices to building management systems and to the cloud? So we have a proposal for how all that can happen. And we'd love to have anyone join who would like to participate in that standard. So to summarize, we believe that realizing the value of the IoT is a very costly proposition, very hard to do. We've talked about why that is. We believe it makes it even worse when you have IoT cloud silos, because now these silos don't communicate either. So we have subsystems that don't communicate, we have cloud silos that don't communicate. The solution is an extensible data and services fabric that interconnects everything to everything, but understands the underlying data model and understands services. So the Landmark IAP standard that Landmark is working on as a web services, open web services standard, we believe solves these problems and really unlocks the value of the IoT for your systems, for your customers. And we'd like to invite you to join the Landmark Web Services Task Group if you'd like to participate more in the development of the standard. Thank you. So, any questions?
What kind of tools do you envision being available, open source tools to manage this and to make it happen?
Can you repeat the question for them?
Okay, yeah, I'll repeat the question for the recording. Greg asked, what sort of tools do we envision being available? One of the things we're very focused on in the development of the standard is using open standards for the IoT. So that's one of the things that IoT focuses on and does very well, is develop some common standards for intercommunicating that make this data fabric possible. So the two protocols that we're focused on are first MQTT, which is a protocol developed for IoT devices for moving data around IoT applications and services and devices. And the other is REST, which is commonly used for websites, web pages. And we heavily leverage both of those standards. And since they are standards, they're widely supported by all development tools. So something we believe is very important is we believe it's critical that there not be proprietary development tools. There shouldn't be any cost to get into this model. You should be able to just go get open source tools, great free tools, things like Visual Studio Code from Microsoft, which is completely free. It's this incredible development environment that costs nothing, right? And you can get Visual Studio Code, you can start writing applications, you can leverage MQTT, you can leverage REST without spending anything. And that's because there's been this huge investment by the IoT community to develop these tools that support these IoT protocols. And so we want to leverage those. So what's it take to get started? Nothing. Download Visual Studio Code, you can start writing code, right? It's that easy and not spend anything. So you can look at the Landmark Web Services standards, see what those interfaces are. You know, we define both the MQTT interfaces as well as REST interfaces. And then you can get free tools. And you don't have to use Visual Studio Code. You can use any of the others that support MQTT and REST. And there's a lot of them available. Eclipse is another one. So there's plenty of tools out there, and yeah, we want to leverage those. Good question, Greg. Thanks. Yes.
Because we don't have access to all the existing field systems, how do you envision handling, addressing, and say duplicate descriptor issues?
Great question. So the question is, since you don't have access always to all the field systems, how do you get access to addressing information, field descriptor information? Yeah, that's a challenge. That's something we're working on, which is really to define how can we do discovery of different protocol devices. For some protocols, it's relatively easy. You know, for BACnet and LAN, it's relatively easy to discover devices, to find how they're set up, how they're installed, and not try to change network addresses, not try to change field descriptors, but bring the information into the system. Other protocols, it's much more complicated. It's like very hard for Modbus to discover an arbitrary Modbus device. So we're working on ways of defining Modbus devices where you do have to know about what devices are in the system, but when you know what devices are in the system, there are ways to at least discover those. So yeah, discovery can be a challenge depending on the underlying protocol. You know, we're defining ways to do it for at least where we can, and yeah, for some kinds of systems, it is going to be difficult.
But I'm also asking, what happens when you do have a duplicate device ID or address? Are you going to, within your fabric, be able to redefine this for the cloud?
Yeah, exactly. Yeah, so the way we define the addressing, it's a sort of a multi-layer address where one of the layers is the protocol, right? So part of the address will say this is a LAN device, or this is a BACnet device, or this is a Modbus device. Then we have a unique descriptor of that device, which isn't the underlying network address of that device. You know, it's one kind of created by the fabric. Yeah, exactly. Yeah, exactly. So so as you said, we create another layer, which is sort of this logical address, and then have a way for, you know, each protocol has its own driver, right? So there's a LAN driver, there's a BACnet driver, there's a Modbus driver. Those drivers know how to do that translation, right? So there's sort of this fabric address, which is, you know, LAN device number, you know, temperature sensor room 3. That's sort of the address at the fabric layer, and then the driver knows how to translate that to, you know, 7.1 node 3, right? Mm-hmm. Yes.
Two questions. Are there any organizations or other organizations developing a similar standard like this, sort of, I would say, a competing standard? The second part is, what's your timeline for hoping to complete this standard?
Great questions. So see, the first one was, are there other competing standards? That's really what I was trying to address here. Yes, there are lots of competing sort of web services standards, but they tend to focus on one or the other dimension, right? They tend to either be single protocol, or they tend to be very general purpose, but not very rich in terms of the data model and the services model. So the Landmark Web Services Standard is the only one I know of that kind of tries to combine both. It tries to be multi-protocol, but also have rich data and services standards. Your second question was about the timeline. We're just now creating sort of the draft proposal. We within Odessa have been working for about 3 years on creating a proposal. It's a pretty big standard, a lot of services, a lot of data. So we're just now putting it into a document for review within the task group. How long that'll take? I don't know, maybe a year, something like that. Rough guess. No questions? Okay, with that, thank you very much.
Excellent.